And this lesson will go up on Bowtie Guy later today.
Yes, sir.
No? I thought that would be popular. Okay, so cracking. Okay, so just before we start cracking, can we have a quick review of? Can we have a quick review of fractional distillation? What happens in fractional distillation? Was that Freddie who came in late? Before we have a quick review of, before we do cracking, let's have a quick review of fractional distillation. What happens in fractional distillation? Just going to bring up a picture here. Oh, okay. Somebody going to talk us through it? Yeah, just sort of start us off, because there's a bit of a story, isn't there, for fractional distillation?
I would say it separates the hydrocarbons based
Okay.
on boiling points.
Separates hydrocarbons based on boiling points. That's a perfect little answer. Can we just sort of talk through the story? What happens first? The crude oil comes in the bottom here. What's happening here? Heating up until. No, we don't want to burn it. That would be bad, and the whole oil refinery would catch fire. We want to heat it up without burning it. Heat it up until it cooks. It's not bake off. No, we'll do cracking in a minute. We'll do the separation in a minute. First, we need to heat it up. Heat it up until it evaporates. Will do. Boils is better. So we heat it to about 370 degrees until most of the oil is turned into vapor, and then it goes into this big tall tower. The tower is temperature controlled, hot at the bottom, cooler at the top. So the vapor goes into the tower. Some of it isn't vapor, some of it's liquid, and it runs out the bottom here. We call that layer bitumen. That's the stuff that's used to make tar, goes onto roads and roofs. But most of the oil is vapor, and it goes into the tower. What happens when it gets into the tower?
It rises.
Rises, okay. And because the tower is temperature controlled, as it rises, it cools. So the vapor goes into the tower, rises, cools, and as it cools, parts of it will
Evaporate.
No, it's already evaporated. The opposite of evaporation. Condense. It'll rise, cool, and condense. Okay. The point at which the vapor condenses will depend on the boiling point of that particular bit of vapor. So if the vapor has a boiling point of, 300 degrees, well, 300 degrees is going to be around here somewhere. It'll condense down the bottom of the tower. But if its boiling point is 100 degrees, it'll keep going up until the temperature drops down below that 100, and it'll condense somewhere up here. So we end up with these different fractions. Each fraction is a mixture of hydrocarbons, but all with roughly the same boiling point. So up here we have what we call the light fractions, things like petrol that go in cars. And then down here we have the heavier fractions, things like fuel oil that go into ships. Okay, that's a quick run through of fractional distillation. The problem with this, the problem with the whole thing about separating crude oil into fractions is the amount of petrol that we get, the light fractions, the stuff up here, is actually quite small. Whereas the amount of heavy oil we get is quite a lot. Most of crude oil is made up of the heavier fractions, and hardly any of it is the lighter fraction stuff. And what do we need the most? There's a lot of cars on the road, and they all need fuel. So this is called a supply and demand problem. The oil that comes out of the ground supplies us with lots of the heavy stuff, but the demand is for the light stuff. And so the chemical industry has to fix this problem, and the way they fix it is with cracking. Okay, so let's just start with that statement. So cracking fixes the the supply and demand problem with crude oil. That being there is not enough. There is not enough petrol produced by fractional distillation. Don't drop into chat, gents. We've got a lot of work to do this morning. You've got your mocks in 2 weeks? Quite soon. Stay focused, thanks. Yeah, after crude oil, yes, yeah. Thank you. Yeah, the supply and demand problem with crude oil, that is that there's not enough petrol produced by fractional distillation. So when the crude oil comes out of our out of the ground and we separate just that raw crude oil, we don't have enough petrol. And the lighter fractions that we need for chemicals and jet fuel and so on, but we get lots of the heavy stuff down here. Okay, so let's just have a reminder about what is it about the fractions that mean that some come up here because they have low boiling points and some down here with high boiling points. What is it that determines the boiling point of a hydrocarbon? What is it that determines the boiling point of a hydrocarbon? Anyone else other than what's your name? Guys at the back? Hello, you're in lesson 2. What is it about these molecules up here that gives them low boiling points?
Is it the saturation?
But we're going to assume they're all saturated for the moment. Saturated just means it's an alkane.
Oh, sorry. Maybe the temperature.
So the temperature determines where the fraction condenses. But what is it that gives? Why does methane have a low boiling point and this whatever it is down here, the fuel oil, has a high boiling point?
They're in different groups.
It's not about groups. Go on.
Carbon.
Be a bit more specific.
Not the amount of carbons in it.
Okay, the amount of carbons in the molecule. Keep paying attention. Right, so if we look at this table here, so the number of carbons, we come right out the top here. This fraction at the top here doesn't condense at all, it's just gas. Those are molecules with 1, 2, 3 or 4 carbons in, molecules that you should know the names of, methane, ethane, propane and butane. You should know how to draw those and you should know their structures. As we go down, the petrol fraction, 5 to 12 carbons in each molecule. Going down, naphtha's the next one, then kerosene, diesel, lubricating oil. By the time we get to fuel oil down here, we've got 30 to 40 carbons in each molecule. The bigger the molecule, the higher the boiling point. Does anyone remember why? Yeah, that's just another way of saying it's got a higher boiling point. Let's just write this up here. Sorry, what am I doing here? Higher boiling point means what? These are all molecules. They're all molecules. Does that help? Okay. stronger. 2 words. One begins with I. Who said that? Thank you. I think 2 people said it. Okay. Stronger intermolecular forces between the molecules. So the bigger molecules have stronger intermolecular forces, so they have higher boiling points, they come out down the bottom. Small molecules, low boiling points, come out at the top. Weak intermolecular forces. Okay. So that means that the stuff down the bottom, the stuff that we have lots of, too much of, the fuel oil, that's made up of big molecules. Right. I'm not going to draw one of these big molecules, 30, 40 carbons. It would take forever. I'm just going to draw a molecule with 4 carbons in. We mentioned that a moment ago. What's the molecule called with 4 carbons in? Remember? Monkeys eat peeled bananas. Methane, ethane, propane. Hello. Sure. Yeah, so 4 carbons is butane, and every carbon always has 4 bonds. So if you put 4 carbons in a line and put 4 bonds around them, you will, and then add a hydrogen to all the other end of the bonds, you will get the right structure for butane. Okay. Right. What we're going to do with that molecule is we're going to heat it up. Well, high temperatures better actually. High temperature. We're going to chuck in a catalyst as well. Mentioned catalysts in the last topic. What does a catalyst do?
Speeds up reaction.
Speeds up a reaction. Great. Okay. The reaction that we're trying to speed up with the high temperature and all of that is to crack. I mean, the word crack kind of suggests what's going to happen next. Remember that we've got lots of small molecules down here. Sorry, lots of big molecules down here. We don't have enough small molecules up there. What do you think cracking does? Breaks them down. That's right. Cracking, when you heat up the molecules to a high temperature, especially with a catalyst, it breaks the molecule. Okay, so I'm going to break the molecule in half. Down the middle there. Please don't write this down because what I'm going to draw doesn't quite make sense. But I'm just going to draw the 2 pieces that we make from that. So if I literally just broke that molecule in half, I'd have 2 pieces. I'd have 2 pieces and they'd look something like that. And neither of those is a molecule. How do we know? Because carbon always has to have 4 bonds. And that carbon there has only got 3. That can't be right. So let's just deal with this one first. How could we make that into a proper molecule where every carbon has 4 bonds? No, it's not going to be ionic, but I like the way you're thinking outside the box there. Well, what does that carbon need in order to make it right, make it a proper molecule? It needs a hydrogen, doesn't it? How about we steal one off that guy over there and give that guy a hydrogen? Now, you should never steal. Thanks. Good social message. Now that carbon has 4 bonds. So it's all right. What molecule is this that I've just drawn? Monkeys eat peeled bananas. 2 carbons. Eth. All right. This one, however, is even worse off because both carbons there only have 3 bonds. So we're going to do something new. We're going to make an extra bond between the two carbons there. It's a carbon-carbon double bond. Now I say it's new because all of the alkanes that we've seen so far have only had carbon-carbon single bonds. We had a word for that, it came up earlier, a word meaning only have single bonds.
Alkene.
No, alkanes
Alkenes.
only have single bonds.
Alcohol.
What's the word for that? It has been used already today in the classroom, begins with S. Say again?
Saturated.
Saturated. Okay. So alkanes, methane, ethane, propane, butane. You can know an alkane by the name ending, like, you know, we all have family names, don't we? So an alkane always ends in ane. That's its family name. So saturated alkanes only have carbon-carbon single bonds. Okay, you probably did this stuff earlier in the course, but it's just a good reminder. So now we've got a molecule here that has a carbon-carbon double bond, so it's not saturated. So we say it is unsaturated. Well done. And it can't be an alkane. Can't be an alkane because it doesn't fit the what we call the general formula. Remember the general formula? If I have N carbons in an alkane, how many hydrogens does it have?
2 plus 3 times 2 plus 2.
Times 2 plus 2, so 2N plus 2. Double it and add 2. So, for example, butane has 4 carbons, double that, 8, add 2, 10, so it must have 10 hydrogens. Ethane, 2 carbons, double it, 4, add 2, 6, so ethane has 6 hydrogens. This doesn't fit that rule. 2 carbons, 4 hydrogens. What rule does it fit? Just times 2, isn't it? That would be CnH2n then. So it's a completely different type of substance. It's not an alkane, it's not saturated. It's unsaturated, and we call it an alkene. So notice that subtle change, it's one letter different, alkane to alkene. Alkane to alkene only differs by one letter, so make sure when you're writing it, if you've got slightly untidy writing, we can really see that A there and that E there. Alkenes only have to have one carbon-carbon double bond. Come back to alkenes in a moment. All right. What are we going to call this? Well, remember our most what is it? Monkeys eat peeled bananas. So 2 carbons must start with eth or F, because that always tells us that we've got 2 carbons, the F. But it can't be ethane because that would make it an alkane. It's an alkene, so it must be ethene. Okay. So again, make sure you write these. Make sure you write these names correctly. All right. So we've got a new compound there, ethene, but it's also a new type of compound that we haven't seen before. Okay, so I've kind of drawn this out, so let's write it as a more conventional kind of chemical reaction. So I've started off over here with C4H10. I've done my cracking reaction, so we have a reaction arrow, and we've gone to make C2H6 ethane and C2H4 ethene. Okay. But the alkenes are different kinds of substance. If I look at what our alkanes are used for, so refinery gas, that consists of methane. What's methane used for? Oh, what's methane used for? Gas? What kind of gas? Pointing at the gas taps there, that's right. Cooking, boilers use methane gas, or gas taps use methane gas. We call it natural gas.
What rocket? Doesn't rocket fuel have methane?
I don't know. There's no reason you can't use methane for rocket fuel. Ethane, I'll come back to ethane in a moment. Propane, what's that used for? Shh. Take part in our conversation, thanks, rather than your own. Propane is used for?
Like gas as well, yeah, obviously.
Fire.
Cooking things.
It's not usually used as camping fuel. Barbecues though, yeah, can use propane.
Like when you go camping, you put it on the barbie, you have a big blue bottle thing in it.
Right, blue bottles are butane.
Right.
The orange bottles are propane. You'll often see, if somebody lives right out in the wilds in the middle of nowhere, they'll often have a big propane cylinder. Often these things are massive by the back of the house.
You get them on like a truck as well, don't you? Because they cause crashes and blowing up. I've seen big propane.
In films all the time, yeah.
On the real life.
Okay, real life, good. Yeah.
How do they do it?
They usually use natural gas for explosions because it's easy to control rather than
They
explosives.
use CGI.
And quite a lot of CGI, yeah. Right, let's get back to the chemistry. And I can't remember what I was saying. What were we doing? Before we got into the explosions? Oh yeah, propane. What was propane used for? Petrol's used for
Cars, fuel.
cars, kerosenes, jet fuel. Right, so quite a lot of these, we're just burning the alkane. We burn methane, we burn propane, we burn butane, we burn petrol, we burn kerosene. They're being burned as fuels. Most alkenes are just used as fuels. Alkenes, however, have a lot of interesting properties, and that's because the carbon-carbon double bond makes them more reactive than the alkane. Okay. Just before we move on, I'm going to give you a couple of little tasks to do. I'll find my... I want you to work out what would be the missing bit here. Let's say I'm cracking a molecule with 8 carbons in it, and one of the 2 pieces that this molecule breaks into has 5 carbons. Can you think about what would be the formula of the other substance that's produced? Just think for a moment. If it's not immediately obvious, then remember, when we have a balanced equation, we've got to have the same number of carbons and hydrogens on both sides. So my 4 carbons become 2 and 2, and my 10 hydrogens become 6 and 4, but on both sides, we always have the same number of each type of atom. What could be the missing molecule on the right here? Could you all have a go at that now and just write it down, and then I'll quickly whiz round.
What about the stuff that does no surface?
Where am I?
Okay. What's the task?
I'd like you to fill in the missing molecule on that reaction on the bottom top border. C8H18 breaks into two pieces. One piece is C5H12. What's the formula for the other piece? Have you got an answer? Grand. If you've done that, can you name the piece that you've just written the formula for? Can you come up with a name for it? Yes. What? We don't say 3 and 6, do we? I need a formula. That's C5H12. That's a formula. Well, then I need a name. You don't need brackets. Have we got a name for it yet?
Yeah, I know brackets.
I didn't think I would.
Think about.
That's gonna have to be like a 3, isn't it?
What you're doing is adding. Right, so what was that before? 3 carbons. But it's not an alkane. Double the number of hydrogens. Yeah, definitely. Okay, so most people have got C3H6. What's it called?
Molecular formula.
Oh, C3H6 is a molecular formula for a compound. What is the compound? What is it? What is it called? All right, do a couple more for me, thanks. On the board, do those now, thanks.
Can't balance it.
Come on, guys. Work on the board, focus on that.
Oh, I wrote C12 and then done the arrow. Sure, you.
Sorry. So the first equation just needs a bit of balancing. The other two equations you need to come up with the product and the reactant for the last one. What most? The first one, the equation's completely balancing. You've got to have the same number of each type of thing on both sides.
Do I take it off on different?
You can't take off anything in balancing. I've got 12 carbons on the left. On the right, I've got 8 plus 2 makes 10. 12 and 10 don't balance. 12 and 12. So, what's an easy way that I can make the right hand side into 12? Well, I can put big numbers in front of stuff, doubling the whole formula.
Oh yeah, and put 2 in front of the C on the right. Is that it?
But it'll double everything in it. It won't just double the carbon, it'll double the hydrogen as well.
8 plus 18 is 26.
Exactly right. So that will balance off all these two. Okay. First one is balancing. Balance by the same number of carbons.
In lockdown, man, was like
What you are you're putting a big number What do I need to do to the first? What do I need to do to the first equation to balance it? Yeah. Say that again. 2 before the C there. That's right. What do I need to do to balance this equation? Oh, sorry. What compound do I need to put in here to balance this equation? C6H14. So we've only got 3 carbons here. We have to make that up to 9. We've only got 6 hydrogens here. We have to make that up to 20. And what hydrocarbon would go on the left here? What alkane would go on the left here? C12?
H26.
H26. Okay. Okay, so really all we're doing when we're balancing cracking equations is making sure we have the same number of carbons and the same number of hydrogens on both sides. The other thing to notice is if we get 2 products, we're always going to get an alkane. We can recognise that's an alkane because 14 is double 6 and add 2. And we're going to get an alkene. We know that's an alkene because 6 is just double 3. If we get lots of products, we'll get 1 alkane, and then all the rest will be alkenes. Okay. One more thing to do, and then we're kind of done. Okay. And that's the test for alkenes. Normally I'd get this out and show you, but we don't really have time today. The test for alkenes is called bromine water. I have this somewhere. Quiet, thanks, Jen. Gents, we can't work and talk at the same time. Quieten it down. The test for alkenes is bromine water. Now, bromine water is a bright orange colour. I don't know why it's called bromine water. It's really bromine solution. It's a tiny amount of bromine dissolved in water. That's all it is. And bromine is orange or dark red. So bromine solution is orange. When I add the bromine water to an alkene, an unsaturated compound, it goes colourless. Not clear, colourless. If I add it to an alkane, nothing happens. So my bromine water turns colourless with alkenes, but remains orange with alkanes. Again, make sure we can read alkenes and alkanes clearly.